Okay, welcome to Chapter 7. Chapter 7 is about matching algorithms. No, we're not talking about online dating. String pattern matching. Okay, so page 212, they start out talk about the standard string pattern matching algorithm. Basically, you're looking for a substring inside a bigger string. That's it. So, I've got a string out there that says Mary had a little lamb. And I'm hunting for the word little. And so this algorithm is going to tell me where physically it is in this thing. So typically it's like an index. So counting at 0, that would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it should show up at 11. Okay? Kind of makes sense. So finding a substring like the word little inside a bigger string, and typically these things stop when they get to the first occurrence. I guess you could tweak one to say, well, go see if you can find a second one or third one, but typically they only just provide you the one. If you wanted an algorithm similar to this that would continue searching, you would just chop up the string. You basically, instead of starting this, you'd start over here in this other position. Same algorithm, it's just where you start. Okay, so a practical application of this in a lot of programming languages is the index of method. So if this was using my favorite language, so if this was like, string, poem equals, right, whatever this thing is, and then I would basically just say poem index of little. And it would return the location where it got found, like at position 11, or some sort of impossible number if it was not found. Now in the book, the impossible number is a 0, but since we starting our arrays at 0, is it possible that the word actually started at the beginning? Well, yeah. So we have to change our impossible value to something like a -1. And that's what this implementation in C# does. It returns the index or a -1 if it's not found. So the approach on how to do this is actually pretty doggone simple. It basically starts right here and says, does that equal to little? No. The L doesn't equal a capital M, so it scoots over 1, tries it again, scoots over 1, tries it again, scoots over 1, tries it again. And that's basically it. There's a little diagram here, so they're hunting for the word they. And so they start up and they go, no, the first, hey, got it. Second letter, woohoo. Third letter, woohoo. Fourth letter, aww. And then it scoots over and scoots over and scoots over and scoots over until finally they all line up. So it took seven string comparisons to be able to get to that location. Actually, behind the scenes, you're probably not doing string comparison. You're doing character comparisons, but that's beside the point. So it took 7 passes, and since they is 4 characters long, I had to have 4 character comparisons times 7. Okay, that kind of makes sense? Okay. So the worst case scenario for this guy would be something like the size of the thing times, so worst case would be I checked every single word every single time for the entire length. So in this case I found it at past 7, but if the length of the thing was 12, it's possible I could go all the way to 12, or dang near. I mean, I can't go off the edge. So the big O notation for this guy is roughly the size of the string times the size of the substring that you're after. Okay, so this is not particularly, it's not horrible, but it's not particularly good. So they show an algorithm on page 213 and 214. Their algorithm, again, their world is a bit weird. They're using like 0 for the return code, and they're starting all their things at 1, and we have to change ours to 0. And there may actually be some other little tweaks to this thing. So Because these things are kind of difficult to visualize, I'm going to go ahead and show you a working copy of this that we can look at in a little bit more detail. So here's the standard algorithm. So here's what I did. I have, the location and the text location and the text start all being 0 rather than they're 1. And then text location less than or equal to the length. I got mine less than the length. And then the sublocation is less than the substring length. That's not exactly what they got here. They got some less than or equal to's and less than or equal to's. I'm not exactly certain why that is. It could just be a typo, or it could be just the fact that when you change it from 0 base to, 1 base to 0 base, you end up with an extra character at the end. And then I'm just comparing, hey, is this character equal to that character? And if it is, move on, move on, move on. Otherwise, then start over. Okay, so this is fairly straightforward stuff. So I'm comparing each character at the location. If you're a Java not, then you're going to have to use this guy, the char at guy. But the text location is that, and if so, then increment, you move on, woohoo! And then start, if it's not, like one of these things does not match, well then I just need to scoot over one and start over. So my text start increments by 1. And then when we finally got to the end of this loop, either you ran out of text or you ran out of substring, one of the two, whichever one happens first. And then you say, hey, if the substring is actually, if the substring location is actually the length, well then, woohoo, we found it. And so we can return that. Otherwise, you return a 1. And that's it. So this algorithm is not bad. But you can probably tell there's an awful lot of slack in here that could be made a little bit better. So let's talk about the problems. Well, the problem in this is that, let's go back to this guy. So I got 3 of them that match, and then the 4th one did not. And so I scooted over 1, and now practically nothing matches. And I went from a success rate of 3 out of 4 to 0 out of 4. Now, the problem might be that if I scoot over just one location, it might actually make worse, right? In this case, I went from 3 correct characters to 0 correct characters, right? So what if I had a little bit of smarts in this and knew how far to scoot over? In other words, somehow I knew that this pattern was not going to exist in here, and therefore instead of scooting it over by 1, I could scoot over by 3 or 4. Okay, that would be a really cool thing if you knew that these matches were not in the pattern. Okay, so if I'm over here with A-R-E, so A doesn't appear in here anywhere, right? Nowhere in my thing I'm looking for. So it doesn't matter if the mismatch A appeared here at T or there or there or there. It doesn't matter. It's never ever gonna match. Not ever, not ever. And therefore, if an A appears in the string, I know darn well I can scoot over 4 positions because there's no chance in heck that an A is ever gonna match my guy. Okay? Good. So on page 215, they have a flight of fancy. They basically said, we could do this with a deterministic finite automaton. Yeah, okay. Kinda. What the heck? What on earth is going on here? How come I can't go backwards? There. All right, so this kind of sort of looks like a finite automaton because you're reading one character at a time. It's not exactly right because I do allow you to keep an awful lot of track keeping. Now, the problem is if I was to use an honest-to-God deterministic finite automaton, then I would have to do an awful lot of work in there in advance. In other words, if I knew the pattern that I was looking for at design time, okay? at design time, that would be pretty doggone easy. But that's just not practical, right? I need to be able to do this at runtime, because when I'm writing the algorithm, I have no idea that I'm looking for the word little. So the whole concept of using an automaton really gets thrown out. Now, we can use some things that kind of sort of look like an automaton. I mean, they're close, but they're not automatons. Okay, and so the first one we talk about is the Knuth-Morris-Pratt, the KMP algorithm on page 215. So this one starts with this original idea. I mean, this part right here looks pretty doggone close. And then we try to figure out how far to scoot over, like that A thing. All right, one more time. If an A appeared in the thing, I know that there is no A in here at all. So therefore, I can scoot over 4 positions. So I have to keep track of those things that are not in my pattern. Okay? And they call these things a fail pattern. That's kind of a funky name. Now, if you're looking at this thing from just a theoretical point of view, there's a success pattern and a fail pattern. The problem is the success pattern really doesn't exist, because the success is just move over 1. Okay? In other words, if you found what you wanted, you moved over 1. I don't consider that a pattern. But, the book does say a success pattern. But, a success pattern is basically just like this one, just scoot over 1. The fail pattern is designed, that's when it does not match, and therefore I need to scoot over 1, 2, 3, maybe 4 positions. Okay, cool. So, how do you do that? Well, let's look at their example in the book. So this is the original one. And then here's how they do it. They say, okay, I'm hunting for A, B, A, B, C. Okay, weird. So if I have a success, then I move to A. And if I have a success, I move to B. And if I have a success, I move to A. But if I fail at this one, then I can go scoot over 2 positions to be able to get to A. If I fail here, then I could go 1 position. If I fail here, I could go 4 positions back. So this is kind of confusing, but basically what we're talking about is when things fail, how far back do I have to go to be able to scoot over, okay? So there's an awful lot of math in showing up how to build this dang fail guy. So this doesn't show the fail pattern, okay? So this looks identical, doesn't it? I mean, dang near. Where I got this, the location for the substring, the location for the string, and if it's not less than or equal to, that part stays the same. And then you basically say, if these things are the same, this is the success pattern, which we've all seen. You just increment the guy. But if you fail, then I want you to go find the location in this array, and that's how many things you're going to scoot over. Cool. So that way, my sublocation is not incremented by 1. It's incremented by this thing. And then the rest is about the same. If the sublocation is greater than or equal to, then return, the length of the string, and then go on about your business. So you might think, well, shoot, that looks pretty good. But the key to this is generating that fail pattern. Because this part, I can easily understand that. I can look at that and go, yeah, I got it. Now, the question is, where did that dang fail guy come from? That's the rub. That's where there's an awful lot of stuff. There's an awful lot of repeat things you have to do. So they build a fail array, and they take this substring, and they just keep seeing if there's any duplicate patterns. I mean, if there's not a duplicate pattern anywhere, then the fail string is kind of easy. But if I have like A, B, A, B, that kind of messes things up. But if I had A, B, C, D, well, then the fail pattern is actually pretty easy to do. Okay, we're coming up on the 15-minute mark.